Well, for those of you who don't know me, my name is Doug Drager. I'm a seismologist in the Department of Earth and Planetary Science and also affiliated with the Berkeley Seismological Laboratory. And in this semester, I'm the acting director of the Berkeley Seismological Laboratory. And I'd like to welcome you all to the 6th annual Lawson lecture, particularly those of you who have come from off campus. This lecture series is named after the late Andrew Lawson, who was instrumental in the building of the Geological Sciences program at Cal at the close of the 19th century. And he's known for many contributions, but is probably best known for orchestrating the geological studies in the aftermath of the great 1906 earthquake and authoring a comprehensive review of the work in 1908, which is now dubbed the Lawson Report. In keeping with this legacy, the Lawson Lecture strives to bring to the public forum leading experts whose research on earthquake hazards is at the cutting edge. And so today we're very pleased to have our very own Professor Roland Burgmann. Professor Burgmann received his PhD in 1993 from Stanford University for his research in geomechanics and crustal deformation. And following some postgraduate work, he taught at UC Davis for several years before joining our department in 1998, where he heads his active tectonics research group. He has a remarkable 97 publications on topics ranging from modeling of co-seismic and post-seismic fault slip in large earthquakes, fault creep on some faults, interseismic deformation, the deformation that takes place between large earthquakes, in other words, fault block, kinematics, evolution of stress, rheological and viscosity structure of the crust, and faulting mechanics. So very diverse body of research. In his research, he utilizes space-based geodetic data, including GPS and synthetic aperture radar, as well as some geochronology techniques to look at exhumed portions of faults. He has worked on tectonics and fault mechanics problems around the globe, including Tibet, Indonesia, Japan, Turkey, Alaska, and of course California, and right in our own backyard. And I'm shaking from his talk, the title of his talk already, A Tectonic Time Bomb in Our Backyard, Earthquake Potential of the Hayward Fault. So let's welcome Roland Burgmann.
Thank you, Doug. Can you all hear me? Microphone's working. Thanks for the kind introduction. I'd also like to thank Peggy Hayward for organizing this lecture series this year, and thank you all for taking some time out of your busy schedules to attend this lecture, which is not meant to scare you, but to provide you with some background information about earthquake potential on the Hayward Fault right in our backyard. So what I'd like to do today is provide some insight into what we know about hazard of the Hayward Fault, what we know about its earthquake history, how it behaves, and how we might better understand the likelihood of future earthquakes. Before I do that, I do want to acknowledge that much of what I show today is thanks to contributions by a large number of former and present graduate students, postdoctoral fellows, and collaborators who over the years have worked with us on related topics. And I'd also like to acknowledge contributions by a number of colleagues, some from the USGS in Menlo Park across the bay, who have provided me with some material that really fleshes out sort of the whole broader picture of what we know about the Hayward Fault. And there obviously has over the years been some financial support from the USGS, the National Science Foundation, and NASA. So I hope that over the next half hour or so, I can provide you with some interesting information and still leave enough time also for you to ask questions, because clearly this is a topic that is of great interest to many of us, not just those of us who do research on the Hayward Fault. Okay, so welcome to the plate boundary. We are, of course, situated on the San Andreas Fault transform, along which the Pacific plate is sliding towards the northwest with respect to the stable North American interior. And this has been going on for 30 million years or so, and probably will continue for many million years. So ultimately, yes, Los Angeles is going to be ruining our views 10 million years hence. The San Andreas Fault is the main player on the plate boundary. It accommodates about half of the budget of slip between the Pacific Plate and the Sierra Nevada, so about 20 millimeters per year. And in fact, it was named and recognized by Andrew Lawson in his early research on the geology of the peninsula, and was named after the San Andreas Valley, which is the valley along Highway 280 that includes San Andreas and Crystal Springs reservoirs. And he also recognized that it was a through-going feature through all of California and seemed to be some major tectonic fault line. The Hayward Fault across the bay is the second most important fault zone. It continues to the north as the Rogers Creek Fault across San Pablo Bay and merges with the Calaveras Fault to the south. And of course, it goes right through our own Berkeley campus, and it forms the boundary of the Berkeley Hills. It really, along much of the length, represents the topographic front of the Berkeley Hills. It also is the reason why the University of California is here, why Cal was established here, because it is the fault that produced the uplift related to producing the hills here that allows for raining off of precipitation and also for the creation of year-round water flowing through Strawberry Creek. And that was a major criteria for the decision in 1868 to found the university right here. And the flat topography that was formed by the offset of the Strawberry Creek Valley by the Hayward Fault in this fashion that you see right here also made for a great place to put a football stadium. And of course, that is still very much a topic of debate now that we are considering retrofitting and extending that construction. Now, the offset of Strawberry Creek shows the overall kinematics of the fault. When you look across the fault from one side to the other side moves to the right. So we call it a right lateral strike-slip fault. And information contained in that offset gives us a measure of how fast the Hayward Fault is slipping. So you can see that all these streams that cross the Hayward Fault north and south of our campus are being offset by varying amounts. Now, Pat Williams, he recognized that this offset of Strawberry Creek, in fact, is also reflected in additional stream valleys right here that used to be former Strawberry Creeks. And then as they were being offset from their source drainage area, they were abandoned. And he was able to find some materials from the abandoned, what is called Mining Circle Creek stream, dated those at 32,000 years old. And so if you assume that 335 meters of offset of the stream that was born straight back then, Strawberry Creek, since then, we get a long-term slip rate averaged over that time of about 10 millimeters per year. So about a quarter of the plate boundary strain is accommodated on the Hayward Fault. And that's an important number to have, of course. So we wouldn't worry about this so much if that motion wouldn't be occurring not smoothly, steadily through time, but occurs episodically in earthquakes. And it was, in fact, observations of the 1906 earthquake, the great San Francisco earthquake that ruptured the San Andreas Fault from San Juan Bautista all the way up to Cape Mendocino, that let Andrew Lawson and colleagues recognize what earthquakes are and how they relate to faults we might see in the geology. So he and G.K. Gilbert and Frank Reed ultimately came up with this idea of elastic rebound, which in his 1922 paper on which he entitled The Prediction of Earthquakes, I have a reprint of it here, he defined earthquakes as being due to slip on eruption in the Earth's crust, which relieves conditions of elastic strain. So there is the idea of if we take this ruler, elastic strain building up, we're deforming the Earth, and eventually there's a breaking point that's reached, and it snaps. And then the whole process begins again. And in fact, he also recognized, because he realized that these faults we have in the Bay Area have accommodated large offsets, such as that of Strawberry Creek and geologic units that have been offset by tens and even hundreds of miles, that the creative amount of displacement we see on a fault today is made up of many, many repeats of these earthquakes. And so that is the elastic rebound theory in the recognition of an earthquake cycle, buildup and release of tectonic strain, elastic strain that keeps evolving. And so then what we feel, let me go back quickly, as an earthquake, the shaking, that's simply a reflection of the grinding and rumbling during the few seconds or minute during which that slip occurs. So in the earthquake cycle, elastic rebound, we have a period of maybe hundreds of years during which strain is building up, broadly distributed, and then in just a few seconds, slip on the fault will occur and will erase the deformation of the adjoining rocks. And Lawson drew that up very nicely in this paper, for example, in this diagram where the fault is right here. He drew this profile of displacement across the fault as it evolves with time, being distributed for most of the time, and then suddenly turning into a sudden step offset during the time of the earthquake. And I added here a scale. The distribution of this deformation is about on the tens of kilometers scale. And the slip curve event in the 1906 earthquake, it was as much as 6-7 meters. For the Hayward fault, we'll see it was somewhat less. So we have an elastic buildup of strain and release. Now, this is occurring only here in California, only in the upper 15 to 20 kilometers. Below that depth, below about 10 miles depth, the Earth is too hot to build up elastic strain, and deformation instead is accommodated by some form of flow, a distributed flow of rocks that over those time scales behave more like a fluid than like a solid. Okay, so the 1868 earthquake, October 21st, was the Great San Francisco earthquake until the 1906 San Andreas earthquake stole its name and obviously revolutionized earthquake science. Based on evidence that was compiled by Andrew Lawson in his 1908 report on the 1906 earthquake, he also worked a lot on trying to provide information about earlier earthquakes. It was recognized that during the earthquake, there was slip from about Fremont to north as far as Oakland and maybe even further to right near here, near Berkeley. Slip was estimated from some measurements to be in the range of 1 to 2 meters. And the magnitude was estimated based on that information to be almost a magnitude 7. So substantial earthquake, similar in size to the 1989 Loma Prieta earthquake, which many of you probably experienced. So if we take the 10 millimeter per year long-term slip rate on the Hayward fault, and we recognize that the last earthquake that ruptured a long portion of that fault slipped by about 1 to 2 meters, then we should have one earthquake every 100 to 200 years. Simple math. And also we would then recognize that to offset Strawberry Creek to its current separation, that took about 170 such earthquakes to produce that. Of course, large earthquakes produce significant damage, and the 1868 earthquake still ranks as one of the most destructive and lethal earthquakes in history. Here are some images from San Francisco and a number of the communities along the East Bay from that earthquake. There were 30 fatalities, and the damage amounts, the cost of the earthquake seem small compared to what we might be facing today. But remember that back then, the population in the Bay Area was much smaller by a very large factor. Okay, so based on the information that I provided you with already, we can make estimates of, well, when should the next earthquake occur, right? We know approximately how much the last earthquake slipped. We know how fast the fault builds up its deformation long term. And with that kind of information and a lot of different estimations of rupture scenarios. Not every earthquake has to be a repeat of 1868. They might rupture smaller or bigger portions of the Hayward Fault. A large working group, the Working Group for California Earthquake Probabilities, provided determined estimates of the probability of an earthquake striking in the next 30 years. And the Hayward Fault, based on the information we have, ranks highest. Together with the Rogers Creek Fault, the probability is 27% that a magnitude 6.7 or larger event will rupture along this fault zone. And for the Southern Hayward Fault itself, the estimate is somewhat less than 20%, maybe as little as 12%. Now, Lawson himself sort of saw the promise here that shouldn't we be able to, if we know how fast the elastic strain is building up and when the last earthquake was, shouldn't we be able to determine when is the next one? If it's just a repeatable, elastic, steady process like a clockwork, we should be able to predict earthquakes. Of course, we know it's not that easy, and these numbers are still awfully uncertain. People are like, well, 30% in the next 30 years, I might be gone by then, even though it could be tomorrow, of course. So what scientists have done is trying to go back further in time to see, are earthquakes in fact more clockwork-like, or are they so random in their occurrence and appearance that it's actually quite difficult to do any better than this. So Jim Linkhamper from the USGS and a large number of colleagues have attempted that on the Hayward Fault. And they found a site at the very end of the Fremont-Bart line, right here in Fremont, near Tyson Lagoon, this is Tulip Pond, where they dug up many, many trenches across the fault to establish the timing of earthquakes that occurred before just the last one that we know historically. So they dig trenches across the fault. They very carefully map out fractures and geologic units in the fault zone, and they are able to date the effect of earthquakes going back from the most recent one back about 2,000 years contained in this record. So as sediments get younger and younger, they experience less and less earthquakes, and you kind of backstrip the earthquake history as it is recorded in this information. That brings us back many, many thousands of years. And because there are datable materials in there that can be dated with carbon-14 age dating, we also know approximately the time at which these earthquakes occurred. So this is the most recent version of the earthquake history that Jim and his colleagues have developed. So we're going from the present back in time about 2,000 years. And the horizontal bars here is the range of ages that best approximate the time of each of these earthquakes. And it certainly looks quite regular in appearance. So there clearly is an appearance of earthquakes happening every 100 to 200 years or so. Now, interestingly, depending on how many of these, how far back in time you go, and you calculate the average recurrence time, if you just take the last 5 earthquakes, you get 138. Now, the last earthquake was 140 years ago, and obviously that caught people's attention. The next earthquake should be 2 years ago. If you go back further in time, that number gets a little bit larger. But most importantly, note the uncertainty in these average recurrence times between large earthquakes. They're plus minus 50, 60 years due to partly the uncertainties of these date ranges and partly due to, in fact, the recurrence intervals being quite variable in time. And so that's why even after we go through this effort of going back in time, we still don't have more solid numbers as to when should the next one be, for sure, based on this past history. So then depending on which of these earthquakes you use to determine when should the next one be, assuming that they're part of a series, you get different estimates of either next year plus minus 55 years and some other possibilities that you see right here. Now for the northern Hayward Fault, there's only one additional site that provides similar kind of information about past earthquakes, which is at the Mira Vista Golf Course in El Cerrito. The golf course gave Jim, Dave Schwartz, and several colleagues only 1 week to dig their trenches, get all the information, collect all the samples and close shop again. So they were able to still conduct a study very similar to the one down near Fremont, making similar kinds of maps, finding evidence that they suggest are due to earthquake deformation at various times. And they find that there were at least 4 large earthquakes during about a similar 2,000-year intervals, maybe as many as 7. And here the estimate of recurrence intervals is quite uncertain. Could be less than 270 years, certainly not more than 700 years. Now, most importantly, there was no earthquake historically since Spanish missions were established here in the late 1700s. They estimate the last earthquake to have occurred after 1640. So it's been 200, 300, if not 400 years since the last evidence for a large earthquake rupture on the northern Hayward Fault. But the Hayward Fault creeps. You probably know that along the Hayward Fault, we find evidence for the fault not just waiting there towards the next earthquake, but actually moving just a little bit each year. So as the fault was started to be developed on, roads crossing the fault and curbs, people noticed just small little things, little offset curbs here. And then as they kept watching those over the years, you can see the same curb moving steadily by some small amount from year to year. And once you start looking, you find that all north to south, from San Pablo Bay to southern Fremont, we find evidence of this kind of motion of the fault at the surface with time. The most famous example being our own Memorial Stadium, where on the south gate you see these offset expansion joints that reflect some deformation across the stadium as well. And throughout the stadium, you find a lot of cracking and deformation that occurred in the 85 years or so since the stadium was built. Jim Linkamper again made a big effort trying to map out all these offset features, dating the age of the feature that was offset and making additional measurements of how that deformation accumulates from year to year, and finds that the surface creep ranges from about 3 millimeters per year, that's near Oakland, to as much as 9 millimeters per year, that's near Fremont. So we have both creep and earthquakes. Clearly the fault can do both, has kind of a schizophrenic nature to it. So there is both this character that a fault can have of being kind of the sleeping hair. It's sitting there, it's slowly building up this elastic strain energy that Lawson suggested was responsible for making earthquakes in the first place. But there are also some faults, at least portions of faults, that slip steadily from year to year very slowly. And clearly we're worried about these and not so much about these. So the Hayward Fault has to be somewhere in between. There's clearly creep all along its surface, but there must be stuck patches below that build up this elastic strain and then rupture again in big earthquakes. So we'd love to know where those are, how big they are, because that helps us then to predict how future earthquakes that rupture those portions of the fault affect the strong motion, the shaking that occurs in a large earthquake. So again, Andrew Lawson was extremely insightful in his early studies and those of colleagues during that time. The recognition of elastic rebound was in large part based on the recognition that the Earth was deformed alongside the 1906 earthquake to a large degree. There wasn't just slip on the fault, there was this elastic strain that goes far away from the fault. And the California Coastal Geodetic Survey realized there was something going on. They had to go back and redo all of their surveys of the coastline and markers in the area. And they found when they compared locations from before the earthquake to those afterwards, that those incurred many meters of displacement due to the earthquake. And then Lawson said, well, then wouldn't it be nice if we could measure that deformation both before and in between earthquakes, and then we could do better in terms of estimating when are we getting close to the breaking point again. And so he suggested what we really need is good geodesy which back then was done with optical triangulation measurements of angles between formed by these monuments that were all located on hillsides in the area. And he tried that for the 1906 San Andreas fault. He looked at data that was collected only before the 1906 earthquake and since, and he suggested, based on motions of Farallon, Point Reyes, and Mount Tam, that the San Andreas fault should be ready to go again 45 years after 1906, so 1950s. Clearly he was wrong, but he had the insight to take that information to make that kind of prediction. He also realized its uncertainty, so we shouldn't be too disappointed that he was somewhat off. Now, back then we had only these very, imprecise terrestrial methods. Nowadays we have what we call space geodesy, one of which you all know, the global positioning system, which helps you navigate your rental car, and when you go hiking or running, you might have a GPS system with you. We can use GPS by setting up somewhat more expensive instruments, collecting data for longer times and processing the data very carefully. We can determine the position of any point at the surface of the Earth with a precision of about 2 millimeters in the horizontal coordinate, relative to some point thousands of kilometers away. So if we set up our tripod and GPS antenna over a benchmark, such as here in Richmond, we take that measurement in 2002, we come back 2 years later, take the measurement again, we'll find that relative to the interior of the North American plate, that monument moved by about 4 centimeters. So we can make a time series of that motion and then ultimately determine a velocity of surface motions. That obviously takes a lot of work to collect these measurements. So a large number of members in our group and volunteers have over the years contributed to collecting these data at monuments throughout the Bay Area in California or other areas that we're interested in. And those are just a subset of the people that have helped with this. So once we've accumulated enough data over a number of years, we have information about the velocity, how fast the point is moving with respect to, let's say, New York. And that is shown right here. So these are about 200 points. This includes points that we observed ourselves, as well as points with data collected by colleagues from the US Geological Survey. And we compiled that information in what we call Bayview, the Bay Area velocity unification. So each of these little arrows indicates how fast the surface of the Earth is moving relative to very far away. And you can see that here in Richmond, we're moving at about 1 inch per year, whereas out here near Farallon, where we're pretty much on the Pacific plate, it's about twice that. Okay, so we now have information about the deformation across the whole Bay Area. We can do that back here at our own Cal Stadium again, where we surveyed 4 points around the perimeter of the stadium. And down here I show the velocities of these 3 points relative to this one here on the west side of the fault. And you can see that these 2 points on the northeastern edge of the stadium move at about 4 millimeters per year, showing that, in fact, we have this very narrow, shallow deformation zone that is responsible for the fracturing that we see in the stadium. Now, before I go on to the analysis of these data, let me show you another type of space geodetic data that, in a way, is even more exciting and promising for this kind of study. PSINSA, which all of you know, is permanent scatterer, interferometric, synthetic aperture, radio detection, and ranging. It's based on having satellites, again, circle around the Earth and taking pictures of the Earth using their own radar wavelength illumination. So the reason why that is exciting, why it's been developed and in general, is it allows you to see at night and through clouds. So it's just an imaging system with its own illumination. Now, what some smart people recognized well after satellites started going into space to take these measurements is that if we compare very carefully the data collected at one time with data that was collected somewhat later, and essentially we subtract the first measurement from the last, we can measure deformation. So we have the satellite, it's bouncing off its energy from the surface of the Earth that comes back, and it uses that to make an image. If by the time the earthquake comes around again, some deformation happens, the distance between the satellite to the ground increases by some small amount or decreases, that signal will return a little bit later or a little bit earlier relative to the last time. So that is something we can, in fact, pull out of these data. And so for every point that you see a color dot here, we were able to determine that through time, these points moved a little bit away. That means they have red colors, or a little bit towards the satellite, reducing the time of travel between the satellite and the ground and back, or increasing it. So this is then a map of we call it range change in distance from the satellite to the ground across the Bay Area. Now, to do this map, we didn't just use one pair of images, but actually 49 acquisitions. And again, we fit a rate to it. So we have, again, a velocity rather than just a snapshot of deformation. So we see, again, across the Bay Area, as we go from these orange colors to dark blue colors, we see this broad change in color. That's, again, the plate tectonic strain across the Bay Area that we also saw with the GPS. But now with the INSAR, instead of having about 200 points, we have 115,000 points in the Bay Area without sending anybody out there with antennas and spending their days babysitting GPS receivers. The advantage is we see much more detail of the deformation. So you might see here along the bay, there are these red areas, very discrete little patches, Alameda, Bayview, Treasure Island. Those are areas that are subsiding, they're settling due to compaction of mostly artificial landfill that was used to increase land area. So here, just two examples. Here's SFO, which you saw had these orange colors, and you can see there are some areas of very rapid, up to about 1 centimeter per year subsidence. There are some parts of the terminal that are going down. So we can see in any detail, even to the point of individual structures, what the deformation is like. Treasure Island is another nice example where essentially the northwest corner of Treasure Island is slowly but surely at about 1 centimeter per year falling back into the bay. If we look back near home, here's campus, here's the stadium, and these again are these reflecting points. Most of those are buildings, some of them are rock outcrops. You can see the Hayward fault right here, this red line. You can see already the change across the fault. There's clearly something happening very discreetly right at the fault. That's the Hayward fault creep. You also see these red plobby zones right here. Those are landslides that also have been sliding every year, and those move as much as 2 inches per year. So that's an additional hazard and aspect of deformation that we were able to detect with this. But most importantly, for what we talk about today, all along the Hayward fault, we see evidence for clear offset, sudden breaks, the surface creep that we also saw in the offset curves along the fault. So then what do we do with these data? What we do is we first try to determine, just by looking at it, well, so where's the elastic strain building up, this stuff, and where is it just sliding along, such as we see at the surface of the Hayward fault? And then we want to go into the subsurface and see if we can illuminate that in more detail. So if we look along the San Andreas fault on the peninsula and to the north, you can see that the velocities very smoothly change across here. Now these are shown with respect to this point, so 0 velocities right here in the center of the bay. So this is clearly the next 1906 time bomb strain building up slowly but surely. If we look again on the San Andreas fault, but here to the south, south of San Juan Bautista, which is here, you can see how the velocity between here and here didn't change at all, and then it jumps to almost no velocity and jumps again to this value. So these two are creeping faults, and as best as we know, the San Andreas fault here does not have the capacity to have big earthquakes. There have never been very large earthquakes along this section of the fault. So here, the motion is truly Planck-like with no significant earthquake hazard that we can determine. So now the question is, how about the Hayward fault? It's somewhere in between, we said. A little bit of this creeping motion certainly at the surface, but also having the capacity for large earthquakes. So we have now these deformation data, both the INSAR and the GPS data, to help us figure out what's going on here. So what we do is we take all the surface deformation data as input into what is a mathematical computer model of how we think fault slip affects surface deformation. So we're assuming the Earth is essentially to first order behaving elastically, just like my ruler. And we're mapping slip on patches down deep below on the Hayward fault to that surface deformation. Each patch of the fault, when it slips, will slightly move every point at the surface. And so we can optimize what is the distribution of slip and locking on the Hayward fault that best matches the deformation that we see at the surface. So with this, we can essentially map out the size and distribution of where the stuck or the stuck asperity or the time bomb is sitting. So here's the latest best answer we have for that. We see that all the way from Fremont, so we're looking from the southeast to the northwest onto the fault from the west. And essentially these purple areas are the parts that we find to be completely stuck. So those are presumably the rupture zones of past and future earthquakes. Now, interestingly, we find that down here near Fremont and also just north of Berkeley, just north of where the 1868 earthquake ended, we don't see very much locking at all deep in our model. There isn't really much locked fault left to have a very big earthquake in and by itself. So if we add up the deficit of slip on these stuck patches on the fault, we can calculate that those ultimately, to catch up again to the full 10 millimeters per year, they need to produce an earthquake of about 6.8 every 100 years or so. So that's the slip deficit rate. And so with the last earthquake having been about 140 years ago, earthquake hazard is indeed high. So this confirms the first order suggestion that the Hayward fault is ready today. It made up the deficit of slip that it had built up since the last earthquake 140 years ago. Now, this is important to know these details because where exactly the fault slips determines in large part what the next earthquake, what earthquakes will produce in terms of shaking. So here on the left is an animation of a model that Dr. Traeger and Sean Lawson did quite some years ago, in which they determined the shaking, as indicated by this color scale, of a Hayward fault earthquake that starts here in the south and moves along propagates along the Hayward fault to the north and doesn't end until much further to the north. And you can see all the shaking is sort of in this area that's being pushed up along the rupture. We call that directivity, where essentially we get the strongest shaking just ahead and along a propagating rupture. Now, this model produces shaking in a distribution that's very different from what was actually experienced in the earthquake. Jack Boatwright just last year did a very careful study of newspaper records, personal recollections of the earthquakes, and determined the intensity of shaking during the earthquake. And he found this very bullseye-like nature of the shaking distribution, very different from this unidirectional, very asymmetric distribution that this particular model suggests. So that suggests the earthquake probably didn't nucleate at the end and moved along it, but nucleated in the middle and moved away from there, and was probably also more limited in its extent to this central region. So given that this is the anniversary of the 1868 earthquake, there's a big effort right now led by Brad Argard at the USGS to develop realistic scenarios that take all this information into consideration as to what might be going on in the future. And so this is just an early realization of an earthquake that is reproduced with a dynamically realistic characterization of its physics and takes into consideration where the fault is creeping, for example, and this limit here to the north where we don't see much evidence for for the capability of significant slip. This is just one example. They're going to do a whole suite of these models to really figure out how can we best explain what happened in 1868 and what are possibilities for future earthquakes, depending on if the earthquake starts in the south, middle, or north. Now, one big question still is, so those parts that we see creeping today, those non-magenta parts right here, will they catch up? They still don't slip at full slip rate. Will they catch up in the earthquake and thereby release the deficit in the earthquake, making the earthquake quite big? Or are they not capable of slipping dynamically, but will catch up as quickly as they can in the hours, weeks, to months afterwards? We don't know the answer for sure, but it's important also because that if the latter is the case, then this evidence for earthquake slip in these trenches on the fault is actually not earthquake slip, but is related to this very rapid slip following the earthquake. Now, we had an earthquake at Parkfield in an area on the San Andreas Fault that was extremely well monitored, so we know the slip and its characteristics very well. And there we did find that the earthquake on a similar fault that has both creeping and stuck patches did not slip the shallow part in the shallower few kilometers of the Earth, but caught up in the weeks to months afterwards. In fact, after about 3 months, the earthquake slip amounted to an earthquake that was 3 times as big as the earthquake that slipped as a magnitude 6 in the seconds of the earthquake rupture. Obviously, where there's hazard, there's risk. Risk, as opposed to hazard, includes the impact on our property and lives. And there have been a number of estimates trying to take into consideration what we know about the Hayward Fault as to what this risk is. And there was one that was just released by a group led by Mary-Louise Sobeck with calculations by a company that specializes on these estimates that produces sort of the latest estimate of risk, economic loss, from a repeat of the 1868 earthquake. And they estimate that the total cost to us, just from residential and commercial structures, no infrastructure, no public buildings, no effects of fire, is about $165 billion. And most scarily, 95% of the cost to our homes is not insured. So that's a little bit scary. In comparison, Katrina, the hurricane, was less damage and there was more insurance coverage of that. So this is obviously something that depends very much on details of what exactly will happen in future earthquakes, and that's why it's quite important to do that kind of work. So then lastly, I go through that very quickly, we still would like to know, well, are these earthquakes more clockwork-like if we really understand what's going on? And so recently, we've come to recognize that faults talk to each other. When the 1906 earthquake happened, it relieved all that elastic strain energy in the crater Bay Area. So all the other faults were kind of like, they let go some of the stress on them. And that was reflected in the earthquake history. Where, for example, this is a slide by Ross Stein from the USGS, in the 75 years before 1906, we had 14 magnitude 6 or larger earthquakes. It was essentially one every 5 to 10 years. In the 75 years after, we had one, and then we had Loma Prieta a little bit afterwards. Maybe that pre-1906 behavior was normal, and all the earthquakes we've had since we really started to develop the area, that was an anomalous stress shadow situation, and we were sort of lulled into a feeling of safety by this occurrence. Now, Fred Politz, a colleague and friend of mine at the USGS, what he tried to do, which I'll quickly summarize, is essentially throw in every earthquake we know happened from various studies in the last 400 years or so, calculated the stresses from these earthquakes, and calculated how stress evolves, taking into consideration this kind of stress interaction, how one earthquake changes the load on another. This is the state of stress right before 1900 with high stress, high hazard indicated here along the San Andreas Fault. Right after the earthquake, we see the stress shadow. And this is today. And here we track the stress through the last 2 earthquake cycles on the Hayward Fault And by today, we have clearly reached the load that previously was sufficient to cause the last 2 earthquakes on the Hayward Fault. If you take this particular model and re-estimate your probabilities, then the number of a Hayward Fault earthquake in the next 30 years goes up to 50% or so. So this is a way to, in more detail, estimate what's going on, what will happen, and it makes the pattern somewhat worse. So there's clearly a need to better understand these kind of interactions. But as a word of caution, another lesson from Parkfield, this is obviously famous for having followed a nice regular pattern, or so it appeared, through a 200-year time period until the last one in 1966. And everybody got excited. The next one is going to be in 1988. Let's really survey it and then know how to predict earthquakes. And it took another 20 years or so to happen. So the Earth doesn't really want to behave the way we think it maybe should. So then Lawson himself, again, in his very wise words, he also said, well, even though there's all this promise here, a disclaimer, I have no intention of predicting earthquakes. We're not really trying to get that far. And he also said what's much more important is to be prepared for earthquake hazard. And he himself had a house built by the famous architect Maybach in the Berkeley Hills, which was a model of earthquake safety. Reinforced concrete, it was supposed to be earthquake-proof and fire-proof. And so clearly, preparing ourselves for earthquakes is ultimately more important than all the science we might be doing for that. There's a lot of information, for example, on the summary page with links to various parts as to how you can prepare for earthquakes. There's an especially nice publication put out some time ago, Putting Down Roots in Earthquake Country, that really walks us through, well, what are the steps that we can take to both prepare our homes, our environments for future earthquakes, and how we might want to be prepared in terms of having earthquake preparedness kits, plans for how to survive for several days after an earthquake, and with a lot of advice on what might be realistic and reasonable things to do, given that we do have our own tectonic time bomb in our backyard. So thanks very much.
Thank you, Roland.
Share this one.
Thank you. Thank you, Roland. And are there any questions for him? My name is Peggy. Doug mentioned my name at the beginning. I've been organizing these talks now for 3 years. And he's here, available. Please.
I was curious where you chose to have your own home compared to the fall.
So the question is, where do you live, Roland?
And whether you purchased earthquake insurance.
I expected that question. I live about 2 blocks from the Hayward Fault, and even closer to one of those landslides that I showed you, but still away from it. I knew already where it was by that time. It's a newly constructed home with all the earthquake engineering that by now are required by code, so that makes me feel a little bit better. We did not get earthquake insurance, given the argument that a lot of people have as to the deductibles being so high, that the question comes up, is the deductible too high to go beyond the likely damage to our particular home? And every year, in fact, this year I was meaning to maybe change my mind, given that I remind myself again and again what's happening. In that earthquake risk cost, right, that 95%, half of that is the deductible. So actually 10% of homes have earthquake insurance, but half of that loss goes into what we pay through our deductibles, or will pay.
More questions, Charlie?
If I throw the trash out the back door, I'm likely to hit the Hayward Fault. I was glad to hear that the chances of surface rupture are not so high here, but does it make much practical difference if you're not actually on the point of ground failure, the amount of ground shaking you get there, or a few hundred yards away? Is the actual fault trace itself, other than going through your foundation, a hazard in itself?
Right, so the question is how bad is it to be right on the fault versus 100 feet away versus maybe half a mile away. You clearly don't want to be on the fault. Even if the slip happens in the hours, weeks afterwards, it will damage your home. As best as I know, and I ask the question a lot to people who work on strong motion, it does not make a large difference exactly what distance you're at. You know, the shaking is essentially saturated over some distance. It makes a huge difference as to what kind of substrate your house is built on. Solid bedrock, much better than soft fill or mobile landslide deposits. So the geology probably makes more difference than just simply distance to the fault.
More questions?
Raymond.
So isn't there evidence in some places with long records for paleoseismicity, like the Dead Sea, that the rate is really not at all constant? It goes through highs and lows, and it may only vary over time periods of centuries, but this idea that one can extrapolate to a steady rate really is not at all supported by the evidence that what little evidence we have.
Right. So Raymond is referring to the observation in a few places where we can push the earthquake record back even further in time, such as the Dead Sea Rift, where they're shaking up sediments in a lake there that give us information about the time of earthquakes back tens of thousands of years. And those appear often clustered, that we have episodes of several earthquakes in relatively short intervals with intermittent periods that are much longer. And there's some observations of that on the San Andreas Fault as well. And there's a huge amount of research now as to, is that what a fault would do if it's completely left to its own devices? Or is this partly a reflection of this interaction, stresses building up and relieving themselves, that reflects how these earthquakes communicate, how larger faults change the distribution of slip and earthquake occurrence? And the answer to that question we still don't know, but it's clearly something that suggests that we need to be not assuming that earthquakes will be just clockworks, and that's certainly what I try to bring across as well.
Yes?
What would be the direction of shaking if you're, say, several kilometers away from the fault? Would it be still parallel to the fault?
That obviously changes very much depending on the character of these earthquake rupture scenarios that come up close to the fault. The shaking presumably will be mostly parallel. But even on a strike-slip fault, there is a component of vertical motion that just comes from the way earthquake waves propagate through the earth. So, but that is another important factor in terms of estimating how structures respond, and it makes a big difference how exactly an earthquake evolves as to what that combination of different components will be.
Yes?
Yes, your question. My question is, your next to the last slide, I believe, showed a 40 to 50% recurrence frequency of Hayward. Is that implying that the USGS working group probabilities don't include short-term frequency considerations for fault ruptures?
So the official estimates by the working group, they do not currently try to take into account, for example, the stress modeling that this study suggests may be important. And that's probably the cautious thing to do. You know, they have votes, should we start to take this into consideration? And right now the answer is we don't know enough about what's going on to do that. The one exception is that there is such a clear recognition of this 1906 stress shadow effect that a certain time dependence of earthquake hazard is incorporated in the most recent estimate. So we're just now starting to go from the translation of science, where we can be a bit more maybe speculative and come up with these high numbers, and translating that into agreed upon expert opinion that is official. And we don't want to confuse the public by every year, going from 20 to 40 back to 20, depending on what we learned about how things work. That wouldn't be very productive.
Having said that, the first working group report was in 1988, I think, just before the Loma Prieta earthquake, and they predicted the highest probability being where the Loma Prieta earthquake happened the next year. The next report came out in 2002, and I think immediately afterwards, the new group constituted itself and is working hard to produce a new assessment based on the most recent science of what the probabilities are. So changes in probabilities don't change based so much on the time since the last earthquake, but more based on how our understanding of earthquakes for the region has improved. Yes? The
What
question
should we be doing the day after?
for drinking water.
Well, we're supposed to have some drinking water at home. There's always drinkable water in your home, in your toilet tanks, in your hot water heater. So there's some water that you have, even though you didn't mean to prepare. What we should be doing is have about, I think, 3 gallons per day for at least 3 days somewhere that you know of, that you, per person, that you can have available for your family. I always have sort of this last resort. I have a water filter, and I can always hike out to Lake Ansa and make my own water and survive. But we should be prepared for that, especially. Yes?
Yes, go ahead.
I'm just curious if there's any effect on the earthquake occurrences because of global warming. Are you seeing any increase in activity?
There's obviously a lot of interest about, so the question was, does global warming change earthquake behavior? The answer is actually yes, in some circumstances. In areas where that stress on fault changes significantly enough due to removal of mass, such as ice sheets melting, so in Alaska, due to water levels dropping along subduction zones along the coastal Earth, people have suggested that both in terms of past occurrence and maybe in the future, there would be an effect on the loading, that elastic stress building up, just a little increment, and therefore on the occurrence of earthquake. There's nothing obvious that just the climate change we're witnessing now, the one that we're mainly responsible for, amounts to much yet in terms of redistributing mass and forces in the Earth to have a big effect, either positive or negative.
Any more questions? Then please join me in thanking Roland for his presentation today.
Thank you.